Innovate.
Educate. This is RTP. This is RTP180. And now, your host, Will Hardison.
Good evening. Welcome. Good to see everybody. How many first-timers? Okay, not too bad. How many came because of the topic? All right, a lot, okay. I gotta be honest with you, at ECU, I do believe it was an elective offered once or twice. Never took it, so nanotechnology, not something I know a ton about, but that's why I love emceeing these events, because it opens up my eyes to a lot of topics that I just don't know anything about. So if you're one of those like me, thanks for coming and engaging and learning this evening. We have three awesome speakers this evening. We're going to mix it up just a little bit if you've been here in the past. So I want to make sure that I go through sort of the updated kind of house rules, if you will. So first off, again, welcome. This is the RTP Frontier building. Just so you know, like normally it's not filled with a bunch of chairs. It's tables and desks and a lot of people working out of here during the day. So during the day, this first floor turns into a co-working area, which is open and free to the public. So if you've got the ability to sort of work remotely or pop in and take a meeting, please come use this space as an area where you can co-work and work out of and take a meeting. All right, presenters usually get 5 minutes. This evening, we're doing 3, and we're gonna give them 8 to 10 minutes. So gonna dive in just a little bit deeper this evening. And of course, like I always say, I am the lovely triangle girl. So we've had 3 or 4 triangles and 3 or 4 different triangle girls, actual ladies doing it. But over the years, we've lost triangles and we've lost a few girls. So you get me dinging into the microphone at the 10-minute mark. So if anybody wants to sponsor a triangle, I think we'd take it. And then Q&A. So I will then take a secondary microphone around and grab 2 to 3 questions per speaker. So please feel free to kind of be thinking of something that you would like to ask. And then, of course, I do know that our speakers, depending upon their schedules and time, always try to at least stick around afterwards to answer any questions and hang out and chat afterwards. We would love for you to be social, but of course, please do it online. RTP180 is the hashtag. So if you would, just get out your smartphone and follow at the RTP, and you can also tweet or use Facebook or Instagram or what have you. And I do know Michael's in the back kind of watching for those hashtags and then replying back. And it's also a great spot if you do have a question and you're not necessarily the one that would raise your hand and ask it in front of 200 people. Maybe we can grab one off of Twitter as well this evening. Of course, throw away your trash. Please keep this place just like you found it, nice and clean and orderly. RTP is very gracious to let us use the space, so the least we can do is thank them by keeping it clean this evening. And then talking. Talking's a big one, kind of a pet peeve of mine. So on the left, on the right, in the back, everyone can kind of hear you. So again, kind of goes back to being social, but do it online. So if you just want to text the person that's next to you or tweet to them, that's perfectly fine. But this room is kind of a hot room, so it's a cement floor, no ceiling. So sound carries very far in this room. So we've got great speakers that are going to pour everything they have into the 10 minutes that they do have. I know I'm setting you all 3 up for just like, they're going to pour everything that they have into the 10 minutes. I'm sorry. But I think you can do it. I think you can do it for sure. So yeah, just be courteous to them, please, and just make sure that you are not talking during their presentations. And that is all that I have for you. I hope that you enjoy these 3 ladies that I'm about to bring up. So first up, we have Daphne Klotze, who has studied physics in the UK and then did postdocs in physics, chemistry, and chemical engineering in Michigan, Harvard, and Cambridge. Her area of physics is soft matter. So in parentheses, I have here gooey stuff like mucus, blood, skin, foams, and gels. Although she wore NC State red this evening, She is the assistant professor at UNC Chapel Hill in the Department of Applied Physics and Science. Sorry, she said I could. She said I could give her a little bit of a hard time about it. All right, please help me bring up Daphne. There you go. Enjoy, have fun.
Hi, good evening, everyone. Can you hear me okay? I guess, yeah, okay, not too loud. So let's start. All right, so today I'm gonna talk to you about a very old problem, specifically how packing polyhedra, which is an ancient mathematical problem, can actually help us design better materials today and actually in nanotechnology. So first I will start by showing you where I am. So this is my group in Chapel Hill. I'm in a new department in Chapel Hill called Applied Physical Sciences, which is, it's a new department, so if you don't know us, check us out. It's really cool. And the work that I'm going to talk about today was done in collaboration with some people shown here. It was mostly between Michigan and Harvard. So I always start my talks with this slide, and this is showing a collection of images that at first glance look very diverse. So they're very different systems. So down here we have nanoparticles. These are watermelons, these are oranges, bottles, red blood cells. So these systems look very different. But actually, I want you to notice that they do have something in common. And that is that they all these pictures show how things fit together in space. So how things pack densely. And packing and the way things pack in space is actually relevant at many length scales. So that means that at small scales over here, these are nanoparticles, so this is nanoscale. Over here, the cells are on the micron scale, but then you have larger things that are on the microscopic scale that we can see. So packing densely in space is relevant at different length scales. And also the way things pack in space affects the properties of your system. So these are things to remember. And in fact, if you look at these images here, these are nanoparticles of different shapes that are packed into nanocrystals. And depending on the structures that they form, depending on the packing, the properties of the material are different. And packing can also affect function or be related to function. So this is not a nanoparticle, these are red blood cells, and when they're healthy, they pack in this way that you can see over here, like Pringles, actually. But when there is a blood clot in the system, they pack very differently, and they have a different shape, which is shown here. They look more like polyhedra. Okay, so you may imagine that the way, like trying to pack objects efficiently in space is a very old problem, and it is. So what dense packings do we know? I'm going to tell you a story about spheres. So sphere is a very simple object because it looks the same from every angle that you look at it. And if you want to know what the densest packing of spheres is, you actually don't have to go very far. So if you go to your local grocery store, or if you try to pack oranges in a crate, you'll probably intuitively do it. So this is the densest packing of spheres. So it's arranged in this way, and this was actually hypothesized a long time ago. So Johannes Kepler, who's a famous physicist, in 1611 made a hypothesis where he hypothesized that this, in fact, this packing that you see here that we all intuitively do and you see in the grocery store is in fact the densest way to pack spheres in space. But, and you can see his drawings here, right? So he was not lucky enough to see the proof of this because, in fact, it took almost 400 years for a mathematical proof for the densest packing of spheres. So Tom Hales, who's a mathematician, in a series of papers showed that this was, in fact, the densest packing. And here he is with tennis balls. Okay, so if we go back to this image, there's something really disturbing about this, which is that, in fact, most objects are not spherical. And if you look around you, most of the objects that you see around are not spherical. So you may think, well, what hope do we have to understand anything if it took 400 years for us to understand how spheres pack in space for more complicated objects? And this is Sort of true, but what we're going to do is we're not going to try to prove things mathematically. We're going to do a combination of computer simulations and math, and we're going to change the shape systematically. So you can see here that if you can imagine that if you take a cube and you round the corners in a continuous way, you can get into a sphere. So what we're going to do is we're going to try to change the shape systematically so that we can make more general statements. Okay. And so here it's going to be a bit tricky, but we're going to try. So what we're going to do is we're going to use polyhedra. Polyhedra are shapes that look like this. So they have flat faces, and the reason, and vertices, so corners and edges, the things that connect the corners. And the reason we're going to use polyhedra is because because they can be synthesized as nanoparticles, and actually nanoparticles naturally grow in polyhedral shapes. So this is a tetrahedron here in the picture, and it's like this. And the way we're going to change the shape is we're going to cut off the corners, snip the corners systematically, okay? And so if we do that, and we do it in a specific way, we get an octahedron, which is the shape here. And I'll follow always with some pictures of nanoparticles that you can see here. Another thing that we can do to the tetrahedron to change the shape is we can shave off the edges. And if we do that, we can get a cube. And then we can fill up the space and we have all these intermediate shapes. So you can get from a tetrahedron to a cube through this operation here. Okay. So what I'm showing here are 25 different shapes, but in fact we did more than 15,000 different polyhedra in this study to really understand how shape affects the packing properties of your system. Okay, so what do we actually do? So we pick one shape, okay? So we do this for all of them. We pick a shape, and then we make a computer simulation. We program a computer simulation where we have our particle. We have a bunch of these particles, the same, so tetrahedron in this case, and we compress it. So as the particles are jiggling about, as we compress the system, they find the densest, the most efficient way to pack. And this is not a super easy process, but this is what we do in the computer simulation. So imagine we take these 3 particles, and we find their densest packings, and this is what they would look like in this case. So, and then we write down what the density is. So the density here is 90% for this packing, the density for this one is 92%, the density here is 98%. So you can see that this is almost filling up space completely. And then, because we're scientists, what we do is we plot these results. And the way we plot it is we have this, we have in the X and Y axes, we have our shape parameters that I was just showing you before. And on the Z axis, we have the maximum density. And so for each of these packings that we found, we make a point on this plot. And this is what it looks like. So this is a surface plot of the packings. And so the packing density here is 1. And what I would like you to notice is that this is a highly complex surface. So it's very smooth here. That corresponds to the area around the cubes. And it's very corrugated over here. And these lines indicate transitions between different types of packings. So you can see this is very rich. Both the value of the density goes up and down, and also there are many lines, which means there are many transitions. If you rotate it, it looks like a spider, and this was a joke in the lab. We called it an alien spider surface. This is because it's symmetric, and it turns out that anything that is symmetric looks like, you know, a biological thing, like a real thing. But why is this important? So this is important because as we're making more progress in nanotechnology, making nanoparticles, synthesizing nanoparticles of different shapes, it's really important to know how shape affects the packing properties. In other words, what we are doing is we're trying to formulate these surface plots are like phase diagrams for shape. So if you have some background in chemistry, phase diagrams are very basic. You don't do experiments knowing only one point. So what we're claiming is that shape space is important. It's important to know what's happening in the neighborhood of your shape in order to design materials with exotic properties, and so on. So I'm going to leave you with one thought today, and that is that for collective phenomena such as packing, shape is no longer a single object. But the way we want to look at it is like one point in a higher dimensional shape space. So something like this. And with this, I will end and take your questions. Thank you.
Awesome. All right. Questions? Don't be shy. I know the first one's always all the way in the back, really?
Hey, how you doing? Great presentation. Just wondered what your applications on the nanoscale are in the near future for this.
On what scale?
The nanoscale.
The nanoscale?
Yeah. What the applications are for this that you're thinking?
So the idea is to provide experimentalists with these kinds of diagrams. There are 2 or 3 basic ideas. One is that if you're doing experiments with these shapes here, we don't know a priori what they're going to pack into. So a lot of, so experimentalists can actually make very complex shapes on the nanoscale, but they don't know what they're going to pack into. So what we are providing is we're telling them what the packings will be. It's like telling them what the crystal they should expect will be. Now, this is one thing. Another thing is that these plots also indicate how sensitive your packing is. So even if you know what your packing is, knowing what happens, so imagine you have a cube and you want to form a cubic lattice, so you form it if you're a perfect cube. What this diagram shows you is also how sensitive you are to deformations, to imperfections in your shape. And so here, it doesn't change that much, but over here, if you have a tetrahedron, you can see that the surface is highly corrugated, so it's very easy to get stuck in other things if you have imperfections.
Oh, that sparked 2 or 3 other ones. I saw your hand first, sir.
Could you give an example of real-world differences in properties with only a minor change in density, in dense packing level? You know, a little bit of change in dense packing causes a huge change.
Well, I mean, so I'm not sure. I'm not sure on the nanoscale if the density itself. So it depends if the density is also related to the actual packing. If the packing changes, you can imagine that the optical properties, for example, change, right? So it may be indirectly related. But as far as density is concerned, like on the macroscopic scale, it's definitely important because you want to pack as many things as you can in a container. So in granular materials, for example, this is really important. You want to have shapes that you don't have voids so that you can pack more material.
So for now, it looks like you're having to determine empirically the phase diagram. Do you imagine that at some point you'll be able to figure out sort of a general equation so you won't have to go through the empirical steps to find out what the packing would be?
Yeah, I think that would be really interesting. That was the original sort of plan, like to make some general rules. I think we have some general rules. They're still, there are some guidelines. So I think there is something deeper about the fact that, for example, this shape over here has this very corrugated surface, whereas this shape doesn't. But it's actually really hard to make very general statements mathematically because we did 15,000 polyhedra, but the number of shapes that exist is infinite. So, you know, thousands is a lot for a paper, but it's not a lot for math. But I think there is something to learn, and there is something deeper. And so I think there's definitely, we can make some empirical rules. I don't think it would be something that would be mathematically covering everything. But yeah, I think there are some rules, yeah. Thank you.
I can help you move these. I don't want to step on them. All right. All right. Next up, we have Claudia Gunch, is the Theodore S. Kennedy Associate Professor of Civil and Environmental Engineering at Duke University. Her research group focuses on investigating the engineering microbiomes in order to improve global environmental health. You ready? You excited? Are you sure? Are you all excited? Yeah, there you go. All right. There you go.
Good evening. This is an exciting evening. I'm hoping to talk to you about what environmental engineers do when we think about nanotechnology. So the work in my research group at Duke, we really focus on a lot of aspects of environmental microbiology. And in the context of nanotechnology, we're interested in understanding what some of the ecological impacts of nanotechnology might be. So today, I'm going to talk to you about microbes and nanotechnology. And specifically, I'm going to talk about silver nanoparticles. Has anybody heard of silver nanoparticles? All right, lots of people. So silver has been used for many years. So all the way going back to 400 BC, people used to use silver. They might not necessarily have understood what silver was actually doing, but they knew that silver acted to kill microbes. And so we've used it over the years to protect burns in newborn eyes, and of course, we have now started incorporating it into a lot of consumer products. And so here I'm showing an increase in the number of products that are on the market that have incorporated nanoparticles, and specifically silver nanoparticles. And you can kind of see there's this exponential increase. And so if you look by breakdown of the actual major materials in these nano products, you can see that silver is one of the most commonly used. And so a lot of you put your hands up when I said, have you heard of silver nanoparticles? And so you might recognize some of these products. One that we often use when we're doing outreach in museum settings is, oops, wrong one, is this little bear, and we've actually done, I think it's a bear, maybe it's a dog, a stuffed animal. So we've actually done lots of experiments looking at it, and one for outreach and explaining how by incorporating these nanoparticles that there are antimicrobial properties that are passed on, but then also talking about the efficacy of these products. And so we've done a lot of work at looking, are these claims of antimicrobial properties actually accurate? And we can, I won't talk a lot about that, but if anybody is interested, I can get into that. So looking at actual properties and how nanoparticles or silver nanoparticles actually carry out these antimicrobial properties, we have a coating. So we have silver nanoparticles that have a specific coating, and the silver shell actually releases ionic silver, and the ionic silver is what provides the major antimicrobial properties. And so the silver is converted to ionic silver, which then binds to proteins that are on the surface of these cells, interrupts functional or important functional properties in the cell. Eventually, there will be damage to the actual membrane, and the cell will open up and lyse, and that eventually will die. And so we are part of SAINT. SAINT is the Center for Environmental Implications of Nanotechnology. It's a joint NSF, National Science Foundation, and EPA center that is joint between Duke, Carnegie Mellon, and several other institutions. And one of the nice aspects of being part of this center was that we synthesized very specific nanoparticles, and a wide range of researchers had an opportunity to study them from different angles. And so the silver nanoparticles that we worked with have citrate coating, PVP coating, and gum arabic coating. And then we did some work looking at these lab synthesized nanoparticles and compared them to consumer products to see if we found similar results. So the work that we do in my lab, as I mentioned, I'm an environmental microbiologist, and a lot of the work that we do has to do with environmental microbiomes. And so these microbial assemblies, I know there was a RTP180 event a while ago on microbiomes, and here I'm talking about environmental microbiomes, specifically wastewater treatment. And so you can imagine those consumer products that I showed, a lot of them, we might consume them in the products, we might wear them and then wash the clothes, and then those particles end up being washed and transported down to the wastewater treatment plant. And so we're interested in understanding how the presence of those nanoparticles impact the performance of biological treatment in those wastewater treatment plants. So we do some work at a variety of different scales, ranging all the way from the fairly simple, meaning in a pure culture with a single microorganisms, all the way to the very complex system where we're looking at the entire microbiome. And so if you were to look at this with a pure culture, so with a single organism, what you would see is that as you increase your concentration of silver nanoparticles, your number of colonies will decrease. So again, confirming the antimicrobial properties of these particles. But a much more interesting question for me as an environmental engineer is in these complex systems, or looking at organisms that carry out specific functions in these systems, what is the impact? And so in wastewater treatment, there's a couple different important functions that take place. The first is nutrient removal. So really here we're talking about nitrogen removal to make sure that when the water is discharged from the wastewater treatment plant, that we don't end up with eutrophication in the resulting waters. And so nitrification is typically the first process that will break down in a system. And then the second aspect has to do with land application. And so the byproduct of a wastewater treatment plant is biosolids, which you can think of as a very rich fertilizer, which then gets applied to agricultural fields. And so some of these compounds end up getting enriched into these biosolids prior to their application. And so I'm going to talk a little bit about the wastewater, the aqueous phase here today. So here you can see this is a picture of Nitrosomonas europaea. This is one of an ammonium oxidizing bacterium. So this is an organism that is able to break down nitrogen. And so this is a very important part of wastewater treatment. And so what we expected to see was, as our silver concentration increased, that we would see a decrease in how those organisms functioned. And we expected that this would be fairly linear, that if we had a certain concentration of ionic silver, that we would see the same impact on those organisms. And so that's what this graph is showing. So it's showing dissolved silver concentrations, so the ionic silver concentrations, and then this is a measure of the actual function of those organisms, so percent reduction nitrification. And so we expected to see something, as I mentioned, linear. So you can see here the PVP coated nanoparticles. Right here you can see kind of this linear reduction. But in fact, what we saw is that while that was true for PVP, some of these other coatings, at a much lower concentration of dissolved silver, we actually see complete inhibition. And so that suggested that there's some other things that are going on. And if you look at these micrographs, so these are actually the same organisms exposed to similar concentrations of these nanoparticles, and you can see that they actually look fairly different. So this is our control. It's a happy cell right here. We expose it to silver nanoparticles. You can see the inside material in that cell starts condensing, so that's why you can start seeing white. With the gum arabic, you see a little bit of that, and you start seeing a detachment actually from the cell wall right here. With the citrate, you actually don't see that condensation, but you see the cell burst open. And then PVP, you see somewhere in the middle. So that suggests that there's some other things that are going on. So that is in a pure culture. So of course, it's nice to study models, but at the end of the day, I want my work to be applied, to be important for things that are happening in complex systems. And so that's what I'm showing here, is that really working in pure cultures is great because they're simple, but really over here is where we want to be in these complex ecosystems. So we set up reactors, and actually here they're nice and pretty because they haven't been filled up yet. And so the idea is replicate a wastewater treatment plant in the lab, so a lab scale reactor. And so we operate these for a period of several months, and then we compared ionic silver to silver nanoparticles to a no silver control, and then compared effects on performance and then also on microbial community. So this is a busy slide, really just getting at performance. So like I said, I'm an engineer. I want to know what is happening in terms of the performance. And so what was striking, or maybe not striking when you think about it, is silver is an antimicrobial, and so you expect that if there are microbes, that silver is going to kill those microbes, and so you would expect a decrease in performance. What we found is that there was there was initially a decrease in performance, but it rebounds very, very quickly. So the performance jumps back up to pre-exposure levels very, very quickly. And so we were interested then in diving down into the microbiome and trying to look at some of maybe the unintended consequences of exposure to these silver nanoparticles. And so this is one way to represent that. So this is a next generation sequencing looking at microbiome community. And each of these different colors represents a different group of these bacteria. And so if you look closely, we can zero in on these dark blue bars right here. And there's this group, the Zuglia beta proteobacteria, that end up getting enriched in these settings. So even though in terms of performance, in terms of function, we don't see a very big impact in the long term, when we start looking at the community structure, we do start seeing some impacts. And so we can break it down a little bit further and zoom in on these organisms, and the organisms that were the most impacted are those that are impacted in nitrogen cycling. And as I mentioned, this is one of those groups where that tend to fail initially. And so Zuglia are particularly important because Zuglia actually play an important role in sludge bulking. And so sludge bulking is something that happens when your sludge blanket doesn't settle very well. And so as a result, your wastewater treatment plant doesn't function as ideally as possible. Now, I present this to you not with a gloomy perspective that everything with silver nanoparticles is going to cause problems, but more in a hopeful way that we actually have tools that are available to us to really look at what the impacts of some of these nanoparticles might be, and nanoparticles and other compounds when we release them, so that ahead of time, we can actually look at what these consequences might be and try to figure out how we might be able to get ahead of any issues. So I will stop with that. This work was performed by, so I've got, this is kind of a chronological perspective of my lab through the years. So as I mentioned, most of this work was performed in the context of SAINT, the Center for the Environmental Implications of Nanotechnology, which is funded by NSF and EPA. And the vast majority of this work was done by Christina Alito, and then Carly Gwynn, who's actually in both of these slides. Mark Wisner, Helen Kim, and Emily Bernhardt contributed also to this work. And with that, I will stop, and I'll be happy to take any questions. Thank you.
Awesome, awesome. All right, I saw one.
Yeah, hi. So my question is on the economics. Like if you're doing consumer products, people are obviously paying for it. But to me, it seems like if you're looking at like wastewater treatment, you're going to need to use a lot of silver that you're not going to be able to recover. And how does that factor into like real world applications of this in settings like that?
So just to make sure I understand your question, are you asking about recovering silver from the wastewater, or are you asking about utilizing silver to control the microbial communities?
Well, for applications in the wastewater treatment, you're using a lot of silver, and if it can't be recovered, then it sounds like it could be a costly process where you're just sending a lot of, as opposed to a consumer product where people are paying for it, and
Right.
the cost is different than industrial scale where you're treating wastewater and the silver is probably just going down the stream with the rest of the effluent.
Yeah, so we're not using the silver nanoparticles to control the microbial communities here. We're trying to figure out when those silver nanoparticles wash off of the consumer products and end up in the wastewater treatment plant. So this is more of an unintended consequence. I agree with you, though. It would be extremely costly to use them in this context. Thank you.
All right, see another hand. I'll do you, sir, and then I saw one more back there.
So you mentioned that the silver is, you showed that graph where you treated the E. coli with silver and then eventually they died when you get to a certain concentration. Is there, have you observed any resistance to the silver?
That's a great question. Yes. So this is another one of these unintended consequences is there are silver resistance genes that have been identified. There's also some other mechanism beyond the silver resistance operon that has been identified. So we actually are working at quantifying silver resistance genes in wastewater treatment. Is one of the research projects that we have. So along those lines, one of the there's some work that actually links metal resistance with antibiotic resistance, and so they tend to be co-located. And so one of these potentially unintended consequences, even though again, right, we don't see any impacts on performance of our treatment, one of the unintended consequences could be the enrichments of antibiotic resistance genes because they tend to be co-located.
They're inherited together.
Yeah.
Cool, thank you.
All right, one more. I saw, unless he stole your question. No? Okay, all right.
Do you have any idea, or is it known, the functional lifespan of any of these different nanoparticles? Do they just continue to build up?
So are you asking in the wastewater treatment plants or just in general?
Anywhere.
Okay. So it's going to vary greatly based off of how they're manufactured. And so this is one of the challenges with doing this type of work and was one of the motivators really behind the center, because we are trying to determine what are potential ecological impacts of nanoparticles that are so wide in range and properties. And so some of these will settle out very quickly, become completely inactive in a matter of seconds, and others will be stable for a long period of time and release the nanoparticle. Now, this is very dependent on the environment that it's on. So if it's, let's say, on a cell phone or if it's on a bench top, it will have very different properties than, let's say, once it gets into a wastewater treatment where it has pretty high ionic strength, and then it'll settle out. So I would say the verdict is still out, and it's very case-by-case dependent.
Awesome job. Thank you so much. Perfect. So for this last speaker, I'm going to do it from over here because it's going to make sense when I read her bio, and I didn't want this song to get too out of control. But we told her we might play a song for her. So Tori Miller is a new assistant professor in the Department of Material Science and Engineering at NC State University. She has been working in metallurgy since she was 16 and is most interested in materials for automotive and aerospace applications. Help me welcome Miss Tori Miller. Everybody knows that's Metallica.
Okay, so thank you very much. So, as stated, I am a metallurgist, which means that I basically I study how we make things out of metal and how we can make things out of metal better to get the best possible set of properties out of the metal. And in particular, my research is in the area of metal forming, which maybe I don't belong here. But the main message of my talk is, first, metallurgists are absolutely nanotechnologists, and in particular, we're some of the first nanotechnologists. Additionally, we're really, really good nanotechnologists because these are the tools we use for nanoengineering. Note the people for scale in these images. So before I go much further along these lines, let me go back about my background a little bit. I grew up in the Detroit area, and in the Detroit area in the 1990s, everyone worked in the auto industry. So when I was 16 and I wanted to get my first job, I went and I got myself a job at Ford Motor Company, doing research and development. So Ford at the time, and to this day, really, really wants to make their vehicles lighter. Because if you can make your vehicles lighter, they're more fuel efficient. So things like the F-150, and this is a Cadillac CTS, and you'd like to switch out things like your conventional steel alloy, which has a density of 7.8 grams per cubic centimeter, for things like aluminum and magnesium, where you can get weight reductions of up to 75%, which would make a huge difference in your miles per gallon. This is doubly important when you go to things like airplanes, because not only do airplanes have to be fuel efficient, they have to, fly. So how, the big question is, when you switch to these much, much lighter alloys, are they going to be strong enough? Are they going to be as strong as the steel that you were previously using? And the answer is absolutely, resoundingly yes, because we nano-engineer them. So these are nanoscale images of two different aluminum alloys. So this one is used primarily for automotive, and this one over here is used both for automotive and aircraft applications. And the light-colored background is your aluminum. And then the dark-colored particles, and I'm going to call these particles precipitates, they're there because they add strength. And they add a lot of strength. In particular, they can double or even triple the strength of your alloy. It's really effective. But to manufacture them and to get it to be effective, you have to get your shape and your size to be right. And again, we're making cars and planes out of these things, so we have to engineer them not, a little chunk of material at a time. We have to engineer them by the ton. So we have a couple of knobs to turn to engineer these nanostructured alloys by the ton. To control the precipitate shape, you can change the chemistry. So this is some aluminum, and then you can chuck in things like magnesium or copper or silicon. And that modifies your shape, and the shape affects how effective it is at strengthening. And then, to change the precipitate size, you play with the furnace, and it's like baking a pie, right? So it's just like that. You can control how long you leave it in the oven. You can control the temperature of your oven. You can, if you've ever made a pie, you can par bake it, so you can bake it in 2 different steps. So there's lots and lots of different knobs to turn. Plus, you can affect your heating rate and your cooling rate, and you get all sorts of different shape and size distributions to really optimize the properties of your light alloys. Historical note, we've been using precipitation hardening for a really long time. So I'm in North Carolina. I just moved here, but I'm in North Carolina now, so I have to talk about the Wright Flyer. So the Wright Flyer got off the ground because they discovered a precipitation hardenable aluminum alloy. So this is the nanostructure of the Wright brothers' crankcase in their engine. And what you can see here, this is a precipitate that is a couple hundred nanometers long and then a few tens of nanometers thick. And you can zoom in a little bit, and you can see that if you look at these are tens of nanometers long and just a few atoms thick. It's really, really effective at strengthening these really lightweight alloys. So this is what I'm going to call a It's a bottom-up approach to material science. We understand now the atom-atom interactions, which allow us to understand the individual defects in the crystal, which allow us to control the scale, the structure at the micro scale. And because we can control the micro scale, we can get really good functional components. And once we have good components, we can build engineering systems that solve real-world problems. So now I'm an assistant professor, and I've got my own research group, and one of my students came with me, and everything is great. And, and I've moved on to working on somewhat more modern aerospace alloys. So these are nickel-based superalloys that we use in modern jet engines. So I'm going to be talking about the components that live here in the hot section, which runs at like 1200 Celsius. It's real toasty. And in particular, I'm going to be talking about these disks right here. So this is the micro scale of these disks. And then if you zoom in and look at the nanoscale, you can see all of these speckles, which again, these are precipitates. This is what allows the alloy to be really strong at these really hot temperatures. But for the past 70 years, these alloys have been plagued by a problem. So sometimes if you get just the wrong conditions, you'll go from your starting structure, which is pretty happy, but if you get a little bit of deformation and a little too much heat, suddenly your microstructure is now a macrostructure. This is a 1 millimeter scale bar, so you could see this with the naked eye. And this is a problem because it runs the risk of something like this happening. So if you can't see that in the back, this is the disk, which is now in pieces. And here's a chunk of it that has escaped a little bit. Now, we're really good at conservative design. This does not happen in service anymore. This happened on the ground while they were doing maintenance because they suspected something was wrong. However, we don't know why this happens, and because we don't know why it happens, we can't avoid it entirely. But my group has a hypothesis. So if you look at this at the atomic scale, there are some interfaces between one phase. This is sort of the matrix, and then this is the precipitate phase. And if you look at the atomic scale interface, there's a fair bit of room in here, and it's kind of misaligned. And because there's room and because it's misaligned, it can move around. And I think sometimes bad things happen, and it moves around and allows the grains to get really, really big. So what if, instead of having it be a little misaligned with lots of room, we lined it up and made it nice and coherent? That seems like would be much, much more resistant to change. But then the question becomes, how do we do that? Well, our theory is we can introduce all of these black lines are a particular type of defect in the atomic stacking. And each of these lines in this micrograph are effectively 1 atom wide. And we think that we can use these defects to shuffle the atoms at the interface, to line up the atoms so that the interfaces can't move anymore. And we think that would be really effective at preventing these problems. Now, of course, how do we make these defects that are 1 atom wide? With a big hammer. It's going to be great. But again, so this is not a solved problem. But we're really excited, and our preliminary results look really good. So we're optimistic about this project and how it's going. But I'm really excited about where I'm at right now, because in the RTNN, and with access to all of the resources, especially things like the analytical instrumentation facility that we've got at NC State, we can go and we can actually get a really good understanding of the atom-atom interactions and the crystal defects. And we can see the atoms in a microscope, which is so cool, because once we get a really good handle on these really small things, we can use it to engineer the big things. And at that point, I can get back to, doing metallurgy with a hammer. So thank you very much.
All right, great job. A couple questions. Come on, there's got to be a metalhead somewhere. Back, yeah, you can go again, that's fine. Just wish you'd sat up front.
Hey, great presentation. Loved how you made a bad guy out of your presentation at that point. Very, very Tim Cook. Do you work with Nanoscribe on printing anything? And then the second part is, do you work with CNTs?
So the answer is, I do not yet work directly with either of those things. We have a really, really amazing resource on the NC State campus, which is the Center for Additive Manufacturing and Logistics, called CAML. So we're hoping that they will start printing some microtruss structures for us, which would be really exciting. In terms of, do I work with any carbon nanotubes? No, but my pet favorite class of alloys is magnesium alloys, because that's what I worked on when I was at Ford. And some of the best magnesium alloys out there are magnesium alloys where you've just stirred in some carbon nanotubes, which is pretty cool.
Any others? Do you think you would have gone down this path had you not grown up in Detroit? Where would you be if you didn't grow up in Detroit?
That's a good question. So the answer is I don't know, but it's like things like when I was a little kid, really little kid, I'd go out in the forest and I'd try to build a fort, right? Except then I'd be like, no, I need something that's both strong but also flexible, and I need something made out of metal.
You kind of always had this.
Oh yeah, no, I was going to be a
in
materials
you.
scientist
Okay.
regardless.
Okay.
I probably would have fallen in love with something, if I'd grown up in Pennsylvania, it would have been steel. It would have been steel all the way.
Sure.
Right?
And they're playing tonight, Pittsburgh Steelers.
Yeah.
So,
Yeah.
Good segue. Last chance question. Yes, sir. All right. One more.
Hi, I used to be a former firefighter, and I know that, fighting vehicle fires with a magnesium engine block, when you put water on it, you're always told to stand back because it's going to explode in your face and kill you. So have they done any studies as far as reactivity with water or flammability with these nanostructures? Does it increase it, decrease it? Does it make things worse or, better for the inhabitants in the vehicle?
So the answer, it depends on what chemistry you add. So in the same way that changing the chemistry by just a little bit can change the shape of the nanoparticles that you precipitate out, in the same way changing the chemistry just a little bit can dramatically reduce the flammability. So one of my favorite classes of alloys is magnesium-calcium alloys, which is really counterintuitive, but you add calcium, which is kind of flammable on its own, but when you add it to magnesium, it makes both of them less flammable. So there are definitely ways to make this much safer.
All right, Tori, thank you so much. Nice job. Very nice job. I'm always very much impressed with the talent that we have in this area. I went to ECU, so I don't really have a dog in a fight like with the three universities, but I do very much respect certainly the talent and the knowledge that comes out of the great universities here in the area. So thanks to you three lovely ladies for coming tonight and giving us your time. How about just one more round of applause? So we do this every third Thursday evening of the month. However, next month, because it does fall so close to a holiday, we will not do it next month, but there is always sort of the end of the year question if 180 will live on. So with that, we will see you next year as we will keep doing 180 going into 2018. We'll see you next year. Have a wonderful holiday season, and we hope to see y'all back next year.